Welcome back, kids. Here we are, Lesson 2, Theoretical and Experimental Probability. We got a few vocab words to start with. First thing, in a uniform probability model, first of all, what does everyone look like when they're in a uniform? They look the same, right? And what does this mean? A uniform probability model, talking about probability, each outcome has an equal probability of happening. Has an equal probability of happening, or the same chance of happening. Two other things. Theoretical probability is what should happen when conducting a probability experiment. So we say theoretically, this is what should happen. And then we have experimental probability is what actually occurs during an experiment. So what should happen and then what actually happens. Let's jump right into some problems. A number cube, or in other words, a dice, is rolled 50 times and the results are shown in the graph below. So let's take a look at this for a moment. Our number cube experiments, the number of rolls and the number showing. So of course on a dice there are 6 numbers and they all have an equal chance of being rolled anytime you let go of the dice. Part A says find the experimental probability of rolling a 2. So that means what actually happened. So the number showing 2, we had 8 of those. And this said this was out of 50 times, so I could add all of these up, but it should equal 50. So 8 out of 50 times, a 2 was actually rolled. As a reminder, with fractions we always simplify, so this can be reduced to 4 out of 25. And I can leave my answer as a fraction. Next one, what's the theoretical probability of rolling a 2? So what should happen? So you have an equal chance of landing on a 1, 2, 3, 4, 5, or 6. So it should be 1 out of 6 chance is how often you should get a 2, or any number for that matter. As a reminder, if I'm going too fast at all, please pause the video. Okay, I'm back. We had a little break there. Had a phone call interruption. So moving on to the next question. How do the answers for A and B compare? If you look ahead, we're going to have another set of questions like this for D, E, and F. So I'm going to do them different ways. And you have options. You can do whichever way you choose. One way we can compare is changing both of the fractions to decimals. So that means I'm going to divide 25 into 4, add a few zeros. And it looks like this is 1600ths as a decimal, which would be exactly 16%. And I'll do the same for 1/6. And if you watch the video, the first video, then this fraction should start looking familiar to you because we found this decimal a few times. Oops, I subtracted wrong. 4, bring down the 0. So I noticed I'm going to keep getting a repeating 6. So 1/6 is 0.16 and the 6 repeats. Or if I wanted to write that as a percent, 16.6 repeating percent. So how do these compare? Well, they're extremely close, 16% to 16.6%. And that's how I'll write my answer. As long as I've shown the work, I've proved it, and they are extremely close. So 1/6 is slightly higher than 4/25. Moving on to the next question. Find the experimental probability of not rolling a 2. So what actually happened, and how many times did we not roll a 2? That means how many times did we roll a 1, a 3, a 4, a 5, and a 6? Well, we could add all of those up from the bar graph above, or maybe a little faster, if I know that I rolled a 2 8 times out of 50, then subtract 50 minus 8 is 42. So 42 times out of the 50 was how often I did not roll a 2. And since these are both even, we can reduce 21 over 25. Moving on to the next one. What's the theoretical probability of not rolling a 2? So what should happen? Well, 5 out of those 6 numbers, that's 5/6. 5/6 of the time is how often I would roll a 1, 3, 4, 5, or 6. Just like 1/6 of the time, I would roll a 2. So again, for problem F, it's saying, how do these answers compare? So let's try it a different way. We saw this at the beginning of chapter 4, and you've been tested on this. One way to prove this is we can make common denominators, or we can do the shortcut in which we're multiplying up. 6 times 21 is 126, and 25 times 5 is 125. That's the shortcut version. 126 is greater than 125, but that's really a shortcut for finding a common denominator. So if I multiply these together, 6 times 25, that's 150. So there's the whole thing. So these again are extremely close. 126 150ths compared to 125 150ths. Again, extremely close. That doesn't mean that always happens just because this was our answer twice. And the last one here, part G, find the experimental probability of rolling a 5. So how many times did we actually roll a 5? Looking back to my table, 5 out of 50 times. And I'm going to reduce that to 1/10. How does that compare to its theoretical probability? So again, theoretically, I should roll each number 1/6 of the time. And you can choose how you want to compare these. 1/10 is 10%, and we know that 1/6 is 16.6 repeating percent. So theoretically, we should roll a 5 a little bit more often than we actually did. And if this was a quiz answer, you need to make sure that you're saying which one was which. So this was our experimental 10%. And theoretically, it should be 16.6%. So it's a little bit higher. We should have rolled it a little more often than we actually did. Moving on to the back side. We have a bar graph, a horizontal bar graph about seasons. Use the results of the survey at the right to answer these questions. What is your favorite season of the year? Spring, summer, fall, winter, or none? I like them all. Part A, what's the experimental probability that a person's favorite season is fall? Write the probability as a fraction. So they're giving us percents. So fall is 25%. But as a fraction, percent means out of 100. So that's 25 out of 100 and reduce it to 1/4. Part B, out of 300 people, how many would you expect to say that fall is their favorite season? So we have a little more work here now. We're trying to assume that 300 people who were asked the same question, that a quarter of them, or 25% of them, would answer the same way. So there are a couple ways, 2, 3, maybe even more ways to do this. We're going to see a variety of ways. So let's try this. We could say 25% of 300 is what we're trying to figure out. Of means times. And we did this in class just the other day. You cannot multiply by a percent. You have to change it to a decimal. So this ball rolls down the hill 2 spaces to the left. So 0.25 times 300. Make sure I have 2 digits behind the decimal point. So 75. 75 sounds reasonable. 75 is 25% of 300. That's one method. We'll try the other one when we get to the next problems. Out of 20 people, how many would you expect to say that they like all of the seasons? So from the survey, that was 10%. So now we have 2 parts to do here. Actually, no. 10% of 20 people is all we're really trying to figure out. 10% of 20. So let's do this one another way. Why don't we change 10% to a fraction? That's 10 out of 100 because it's a percent. And I can reduce that to 1/10 to make my work easier with smaller numbers. So 1/10 times 20. And you can put 20 over 1 and multiply straight across. And that becomes 2. So does that seem reasonable? 2 people are 10% of 20. Yes, that seems reasonable. And one more. Out of 650 people, how many more would you expect to say that they like summer more than they like winter? So we have a comparison. 39% of people like summer and 13% like winter. So I'm going to just subtract these two to compare, because I can say right away that 26% more people prefer summer. So 39% minus 13% is first giving me 26%. So we're really trying to find what is 26% of 650 people. You can take your pick which way you want to do it. I prefer to do percents usually, or decimals, times 650. But if you like fractions, you can try it that way too. So I'm going to set up 650 times 2600, making it a decimal, and multiply and see what we get. So remember that you should always check your answer for reasonableness. For example, if I forgot my numbers, my digits behind the decimal point, 16,900 is not a reasonable answer for this. I need two numbers behind the decimal point. 169 people is 26% of 650. That sounds reasonable. There we go. When I see you in class next time, we'll be talking about theoretical and experimental probability, and there may be candy involved. See you then.